Many count variables in medicine and biology come from repeating the same experiment over and over. Each time we perform a trial, there are only two possible outcomes, success or failure. If we repeat this process a fixed number of times and the probability of success stays the same, the number of successes follows what we call a binomial distribution. The binomial model is one of the most important probability distributions because it captures a wide range of real-world scenarios involving counts of events. We denote a binomial random variable as x distributed as binomial with values n and p. Here, n represents the number of trials, and p represents the probability of success on each trial. The random variable x counts how many successes occur out of those trials. This notation immediately tells us both the structure of the experiment and the probability model we will use to analyze outcomes. Before applying the binomial model, we must check several conditions. First, the number of trials must be fixed in advance. Second, each trial must produce only two outcomes, typically labeled success or failure. Third, the probability of success must remain constant from trial to trial. Fourth, the trials must be independent, meaning the result of one trial does not affect another. These conditions ensure the binomial formula applies correctly. Let's motivate the binomial distribution with an example involving a claim of extrasensory perception. John Doe attempts to guess a number chosen at random from 1 to 5. The experiment is repeated 3 times. Each guess is either correct or incorrect, so each trial naturally fits the success-failure framework. If John is simply guessing, the probability of success on any one trial is 1 out of 5, or 0.2. We define the random variable x as the number of correct guesses in 3 trials. Since there are 3 trials, x can take values 0, 1, 2, or 3. Each trial is independent, and the probability of success remains constant at 0.2. This setup matches the conditions required for a binomial model, making it a perfect example to introduce the distribution. Suppose we want the probability that John gets exactly 2 guesses correct. There are 3 possible sequences that produce 2 successes: S, SF, SFS, and FSS. Each sequence has probability 0.2 squared times 0.8, since 2 successes and 1 failure occur. The probability of each sequence is 0.032, and because these outcomes are mutually exclusive, we add them together. Adding the 3 possibilities gives a total probability of 3 times 0.032, which equals to 0.096. This process works for small experiments, but as the number of trials grows, listing every possible outcome becomes tedious. We need a general formula that automatically counts how many ways successes can occur without writing out all sequences. The binomial probability formula solves this problem. The probability of exactly x successes in n trials is given by the binomial formula, which includes a binomial coefficient to count arrangements, multiplied by the probability of successes and failures. This single formula lets us compute probabilities efficiently for any number of trials. Binomial coefficient, written as n choose x, counts the number of ways to arrange x successes among n trials. It is calculated using factorials. This term handles the counting aspect, while the probability terms, p raised to the x and 1 minus p raised to n minus x, account for the likelihood of each arrangement. Together, they produce the full binomial probability. Let's use the formula to find the probability of exactly 1 correct guess in the ESP example. We substitute n equal 3, x equal 1, and p equal to 0.2. After evaluating the coefficient and probability terms, the result is 0.384. This demonstrates how the formula replaces the tedious process of listing outcomes and adding probabilities manually. Before using a binomial model in practice, always verify the conditions. Ask yourself, are outcomes binary? Is the probability of success constant? Is the number of trials fixed? Are trials independent? Missing one of these assumptions can lead to incorrect conclusions. So checking the conditions is an essential step in every binomial problem. One common situation where the conditions fail is sampling without replacement from a small population. In this case, probabilities change from one draw to the next, violating independence. However, if the sample size is less than about 10% of the population, the change is small, and the binomial model often provides a good approximation. This practical guideline is widely used in real applications. Just like any distribution, the binomial distribution has a mean and standard deviation. While the expected value can be derived from the general formula for discrete random variables, the result simplifies nicely. For a binomial random variable, the mean is simply n times p. This tells us the long-run average number of successes across many repetitions of the experiment. The variance of a binomial random variable also has a simple form. It equals n times p times q, where q equals 1 minus p. The standard deviation is the square root of this quantity. These formulas allow us to quickly describe both the center and spread of a binomial distribution without computing long sums. Now consider example 1 involving vaccine side effects. 10 volunteers each have a 0.2 probability of experiencing a side effect. The number of side effects follows a binomial distribution with parameters n equal to 10 and p equal to 0.2. Using the binomial formula, we can compute probabilities for any specific number of side effects. For example, the probability of exactly 3 side effects is found by substituting into the binomial formula. The calculation yields approximately 0.2013. We also compute the expected number of side effects as 10 times 0.2, which equals to 2, and the standard deviation as the square root of 10 times 0.2 times 0.8, which is about 1.265. These summary values help us understand the typical behavior of the trial. A bar chart of the binomial distribution shows that most probability mass is centered near 2 side effects, which matches the expected value. The shape of the distribution helps visualize how likely different counts are. This graphical view complements the formula and reinforces intuition about where outcomes are concentrated. In example 2, we examine gene carriers in a plant population where the allele appears in 10% of plants. Sampling 12 plants gives a binomial model with n equal to 12 and p equal to 0.1. The expected number of carriers is 1.2, and the standard deviation is about 1.039. These values describe the center and variability of the number of carriers we expect to observe. Sometimes we are interested in probabilities like at least 1. Using the complement rule makes these easier. Instead of adding many probabilities, we calculate 1 minus the probability of 0 successes. In this case, the probability of at least one carrier is about 0.717, meaning there is a 71.7% chance of finding at least one carrier among 12 plants. Example 3 considers counting positive assay results. If each fruit fly has a 0.3 probability of having a gene, and we test 6 flies, the number of positives follows a binomial distribution. The probability table can be computed using the formula or software. This example shows how flexible the binomial model is across different biological contexts. The main idea to remember is that the binomial distribution models counts of successes in repeated independent trials with constant probability. It provides formulas for probabilities, mean, and standard deviation, allowing us to describe both the likelihood of specific outcomes and the overall behavior of the process. This distribution becomes the foundation for many statistical models you will encounter in later videos.